1, okay, which now gives us a nice value here again. Well, if these can be assumed to be nice, so therefore we have c must be equal to, well, now we end up with a root 5 plus 1 over 2 root 5. So now our general solution, okay, okay, to the Fibonacci recurrence, okay, okay, the Fibonacci recurrence, don't forget, we have, excuse me, we already estimated so far, okay, so it must be an is equal to the c value, we just calculated c, to be root 5 plus 1 over 2 root 5, which needs to be multiplied by 1 plus root 5 over 2 raised to the power of n, okay? Plus the d value, well, we know what d is, so it's plus d, which is root 5 minus 1 over 2 root 5, okay? Times, well, the R2 was 1 minus root 5 over 2 raised to the power of n. So this here is our general solution now to the Fibonacci sequence. Now what we could do is we could start estimating things. Let's just see, sanity check this. What about A0? Okay. Well, A0, so n is 0, becomes let's say root 5 plus 1 over 2 root 5 times any number raised to 0 is just 1, so that stays there. Plus, once again, minus 1 minus root 5 over 2 raised to 0 is just going to be 1. So this leaves us with root 5 minus 1 over 2 root 5. Okay, and look, this becomes A0 is, well, we end up with 2 root 5 as the denominator. This becomes root 5 plus 1 plus root 5 minus 1. Oh, what does that give us? That gives us 2 root 5 over 2 root 5, which is equal to 1. So we know it works for the first term in the sequence at index 0. What about the next term? Let's just have a look there. Okay. So maybe what I'll do is I'll just fold this over a small bit here. Okay, so that we still have our general solution. So what about A1? So A1 must be this time n becomes 1, so it's root 5 plus 1 over 2 root 5 times 1 plus root 5 over 2 plus it's root 5 minus 1 over 2 root 5 times this thing here raised to the power of 1, which becomes 1 minus root 5 over 2. Okay. And if we just multiply out, well, what do we end up with here? We end up with this is A1 must be equal to 2 times 2 gives us 4. So that gives us a 4 root 5. And we're going to end up with 4 root 5 over here. So let's just see 4 root 5. Root 5 times 1 gives us a root 5. Root 5 times root 5 gives us a plus 5. 1 times 1 gives us a 1. And 1 times root 5 gives us a plus root 5. Plus, over here, we end up with 2 root 5 times 2 gives us 4 root 5. And we end up with root 5 times a 1 gives us a root 5. A root 5 times a minus root 5 gives us a minus 5. And minus 1 times a 1 gives us a minus 1. And minus 1 times a root 5 gives us a plus root 5. So now we have A1 must be equal to, what we got over here? We have 2 root 5 plus 6 over 4 root 5. Plus over here we have 2 root 5 minus 6 over 4 root 5. And what we end up with is A1 is equal to a common denominator of 4 root 5. That gives us 2 root 5 plus 6 plus 2 root 5 minus 6. And voila, A1 is 4 root 5 over 4 root 5, which is equal to 1. So we now know, well, we could continue, okay, we could continue this particular process. It just gets a little bit, it gets very, very complicated when, not complicated, but it gets very, very, let's say, laborious when n becomes even a bigger number because we have to expand these particular terms out. Okay. But irrespective of that, so we can see that this particular general solution looks very complicated looking. Okay? Actually, an amazing thing about it is that we have surds here. Okay, so we have all of these roots. Okay, and we know that the Fibonacci sequence itself is just natural numbers. And so it's amazing that this, as n gets larger and larger, okay, that this thing here it just reduces down to a natural number. So actually, this thing here is always a natural number. When you put in any n value, you'll always get a natural number, which I think is an amazing thing and has been commented, I'm sure, many times in the literature with respect to this particular problem. But irrespective of that, what we've done here is another video in a series of videos dealing with recurrence relations. We've looked at identifying the closed form solution for the Fibonacci recurrence relation, which relies upon the characteristic polynomial. To get R1 or 2, we need a characteristic polynomial, which in the Fibonacci case, our constants, our coefficients are ones. So our characteristic polynomial can't be solved using the rational root test. So we need to use the quadratic formula, which ends up with these particular roots that look pretty nasty looking. But you can see what we end up with is we end up with a closed form solution to that particular recurrence. Okay, guys, once again, this is Jonathan Lambert with Maths and Stats. I hope that this video was in some way intuitive. And more importantly, I hope that was helpful to you. And thanks for watching. Okay, bye-bye.